Today we'll be solving the following system of differential equations. We have dx dt equals y and dy dt equals x plus y. And to start off, we will define a matrix. We'll call it A, and it's equal to 0, 1, 1, 1. And we'll have the following expression. We have dx dt, dy dt is equal to this matrix 0, 1, 1, 1 times our solution x, y. And to solve this system of differential equations, we'll consider the characteristic polynomial. So first, we have to consider a minus lambda I, where I is the identity matrix. So we're going to have 0, 1, 1, 1 minus lambda 1, 0, 0, 1. So this is equal to 0, 1, 1, 1 minus lambda 0, 0, lambda. Subtracting these two matrices, we have negative lambda 1, 1, and we have a 1 minus lambda. So we have a minus lambda I is equal to this matrix, and now we want to find the determinant of a minus lambda I. So the determinant of a minus lambda I is equal to negative lambda times 1 minus lambda minus 1, and we want to set this equal to 0. So when we set this equal to 0 and simplify, we're going to have a negative lambda plus lambda squared minus 1 equals 0. We can rearrange this as lambda squared minus lambda minus 1 equals 0. And we have to solve this trinomial for lambda. And if we do that, we have lambda is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a, but that's just divided by 2. So we're going to have lambda is equal to 1 plus or minus the square root 1 plus 4 divided by 2. So we have lambda is 1 plus or minus the square root of 5 over 2. So we have lambda 1 is 1 plus the square root of 5 over 2, and lambda 2 is 1 minus the square root of 5 over 2. But we recognize lambda 1, and lambda 1 is just the golden ratio. So if we know lambda 1 is the golden ratio, and the golden ratio is 1 plus the square root of 5 over 2, by some rearranging, we have 2 phi minus 1 is the square root of 5, and we could plug it into this one. So we have lambda 2 is 1 minus 2 phi minus 1 divided by 2, which is 1 minus 2 phi plus 1 divided by 2. So we have lambda 2 is 2 minus 2 phi divided by 2, which is equal to 1 minus phi. So we found out the eigenvalues. We have lambda 1 is phi, and lambda 2 is equal to 1 minus phi. So now picking up where we left off, we determined that the eigenvalues are lambda 1 equals phi, and lambda 2 is equal to 1 minus phi. And now we want to consider a minus lambda 1 I times a vector x. When is this equal to 0? So now plugging in lambda 1 is equal to phi into this expression, we're going to have a minus phi I x is equal to 0. But all we have to do is just plug in phi here. So we're going to have negative phi 1, 1, 1 minus phi times x1, x2 is equal to the 0 vector 0, 0. So now multiplying this matrix times this vector, we're going to have minus phi x1 plus x2 is equal to 0. And we're going to have x1 plus x2 times 1 minus phi is equal to 0. So solving for one of these, we're going to have phi x1 is equal to x2. So we'll choose x1 equal 1 over phi, and we'll choose x2 is equal to 1. So the corresponding eigenvector x will be 1 over phi 1 for lambda 1 is equal to phi. So now that we found this eigenvector, we have to do the same thing for lambda 2 equals 1 minus phi. So we want a minus 1 minus phi I y is equal to 0. Then we're going to have negative 1 minus phi 1 1 1 minus 1 minus phi y1 y2 is equal to the 0 vector 0 0. So we're going to have a phi minus 1 1 1, and then we're going to have phi times y1 y2 is equal to the 0 vector. And then doing the same procedure as before, we're going to have y1 times phi minus 1 plus y2 equals 0. And we're going to have y1 plus phi y2 is equal to 0. So again, solving for one of these, we're going to have phi y2 is equal to negative y1. So we'll choose y1 equal 1. And so that means that y2 is equal to minus 1 over phi. So the corresponding eigenvector for lambda 2 is y is equal to 1 minus 1 phi. So now that we have our eigenvectors, so we have x is 1 over phi 1, and y is 1 minus 1 over phi. We have lambda 1 is phi, and lambda 2 is equal to 1 minus phi. So now that we have these components, then our solution to the system of differential equations, x of t, y of t, is equal to c1 e to the lambda 1 t times the eigenvector x plus c2 e to the lambda 2t times the eigenvector y. So now that we have all these components, we could just plug it in here. So our solution, x of t, y of t, is equal to c1 e to the lambda 1 phi t, and the corresponding eigenvector is 1 over phi 1 plus c2 e to the lambda 2, but that's just 1 minus phi t, times that corresponding eigenvector, which is 1 minus 1 over phi. So now we could say that the solution is x of t is equal to c1 times 1 over phi e to the phi t, and we have plus c2 e to the 1 minus phi times t, and we're going to have y of t is c1 e to the phi t, and we'll have a minus c2 over phi e to the 1 minus phi times t. And so that is the solution to the system of differential equations. Thank you very much for watching.